Dr. Anna Peltseva. I'm a new professor at Purdue University in Indiana, but the last 4 years I spent in Louisiana, University of Louisiana at Lafayette. Some of you met me even before that when I did my PhD in New York City, and I met an incredible team of USDA soil scientists in Louisiana, and now I'm meeting more in Indiana. So I'm really grateful for your support throughout my years working with USDA, and I'm beyond honored and grateful for USDA giving us the opportunity to do research and fund my student, Eriell Jenkins, who will give this webinar today as part of our deliverables for the grant that we received 2 years ago. The overall goal of the grant was to understand how we can use portable XRF fluorescent technology in urban spaces, specifically for urban soils. And we also had a couple case studies. One is in Chicago. We're working on a paper to analyzing soil in some parks and see what are the trace elemental concentration, how we can promote urban agriculture. And the other case is in St. Louis. We work with Ralph Tucker and ongoing soil survey of St. Louis. So Eriell is testing multiple samples, different soil profiles, and we will work on this manuscript next year. But in today's presentation, Eriell will talk about XRF review, what she found specifically in 67 articles that used XRF in urban studies, urban soil studies. So she will tell you how she picked those particular articles, based on what criteria. We have a preprint that is now available for feedback. I shared with you in the email. You can send me a feedback so we can incorporate into our draft, and we will work on them. Improving the preprint, making it an article in the next few months. So your feedback is welcome. So Eriell is graduating this month. It's her last assignment to present, and she already presented this work at the NCSS conference we had in Lafayette, Louisiana in May. She presented this in Soul Society of America last month in San Antonio. So, but we really wanted to share with the USDA offices who are interested in using XRF. Some of you may already have experience, but I think it will be a very valuable exchange. Eriell will speak for 45 minutes, and then we will open a Q&A, so you can ask questions in the chat, or maybe I will be able to let you talk if the feature allows me on this webinar. But feel free to exchange ideas in the chat, comment, write, ask questions, and we will address it all at the end of the presentation. We will try to finish it within an hour. Thank you so much for joining, and the floor is yours, Eriell.
Yeah, thank you guys so much for joining. I really appreciate you being here and for being interested in my research. And it's really nice to meet you guys, and I look forward to hearing your feedback on my presentation today. So to start off, it's important for us to talk about urban agriculture. Green spaces like rooftop gardens, community gardens, and parks, they enhance social, economic, and health aspects of gardeners, farmers, and most importantly, the people in the surrounding communities. Community gardening can even increase fruit and vegetable consumption by a factor of 1.4 to 3.5 times. They enhance community aesthetics, they increase biodiversity, improve social cohesion, increase home values. They decrease carbon in the atmosphere and can convert brownfields, which is land that is abandoned and underutilized due to pollution from industrial use, to a productive land use. And most importantly, urban agriculture is a great way for local food sourcing in cities, especially places with food deserts. And it's a great opportunity to educate a lot of people in these communities. They gained popularity in the mid 1800s Community gardens, they kind of started out during economic depressions and wartime efforts to retain as an effort to retain community access to food when it was scarce, and they serve critical roles for people during crises. So over time, they've continued to evolve, and in response to industrialization and growing urbanization, they've been incredibly successful in places like West Philadelphia, which is and they have like completely transformed economically depressed areas by improving residents' access to nutritious food, enhancing physical and mental health, and fostering community engagement, and of course, leading to a lot of education in these communities that don't know very much about sustainable practices, particularly for urban youth. And it has helped enhance environmental stewardship in areas that otherwise wouldn't have had that type of had exposure to this type of thing. So as great as community gardens are, as well as urban green spaces, heavy metal contamination is a big threat to human health, especially for vulnerable communities like children. Heavy metal contamination is normally the result of anthropogenic factors like vehicle and industrial emissions, paint, historical pesticide and biocide use, waste dumping. We're talking heavy metals such as lead, arsenic, nickel, copper, zinc, manganese, and chromium, and more, which can lead to a variety of health problems, of course, such as gastrointestinal and kidney dysfunction, nervous system disorders, skin lesions, vascular damage, immune system dysfunction, birth defects, and even cancer. The way that we measure these heavy metals in laboratories in urban soil specifically, there's a couple different methods, such as inductively coupled plasma, which requires samples to be in a liquid form, acid digestion, which includes the use of strong acids, which is typically a mixture of nitric acid and hydrochloric acid, and sometimes hydrofluoric acid, depending on the matrix and the metals that are present, and X-ray diffraction, which can be quite expensive, which is something that we're going to go through in a second. So another way of testing for these heavy metals, a newer way, especially in regard to this particular research, urban soil studies, is the use of the portable X-ray fluorescence analyzer. It operates basically by utilizing X-rays that are generated by an X-ray tube within the analyzer. The emitted X-ray beam interacts with the atoms in the sample, and it causes the displacement of inner shell electrons. So upon this displacement, the atom, of course, becomes momentarily unstable, and seeking to rectify this, it starts trying to fill the vacancies of electrons left behind. So that process is known as fluorescence, and it involves electrons from higher orbits moving down to occupy the lower orbits, and the energy that's lost during this transition is specific to the distance between the electron shells, which is also unique for each element. And this is how the instrument can identify the elements and provide a detailed analysis of the elements within the material. So here is a graphical abstract. So just to like preface what we're going to talk to today, some of the pros of in situ, which is in the field use of the PXRF rapid results, no sample preparation required, on-site analysis, of course. Cons, sometimes the results can be affected by moisture. They can be less accurate. There's limited depth. Environments you can use them in, of course, urban areas, industrial sites, contaminated land. X-I2 analysis, it's it typically has higher accuracy. It's in a controlled environment. The analysis can be more detailed. It's more time consuming. Sample preparation, of course, is required, but so you don't get rapid results. And this can be done in research labs, university labs, environmental agencies, etc. So some of the advantages right off the bat with the PXRF, traditional laboratory analysis, um, like we talked about, the atomic absorption spectrometry, inductively coupled plasma. These methods are typically very time consuming with preparation. You have to deal with things like acids, and it can sometimes take days to be able to test the samples that you're wanting to test. They're also quite expensive. The PXRF itself is a lot more affordable considering it can be anywhere from $15,000 to $50,000, which is a lot of money, but in comparison to spending 100,000 to $500,000 for other types of analyses, it can be a much more affordable option. These methods, the traditional methods, are also destructive to the sample. With the PXRF, you can basically use the same sample and test it over and over again, and it won't be chemically altered by acids. So you'll be able to test as many times as you like. Um, it offers real-time results, of course. You can get 20 to 23 chemical elements of concern simultaneously. And of course, it's versatile. You can use it in the lab or in the field. And X-rays themselves, there is training that comes with having to use this instrument, of course, but in some ways it can be safer than dealing with acids that can be very damaging to you. So some goals of this literature review going in, we wanted to assess literature on these analyzers to determine their accuracy and precision in analyzing heavy metalloids in urban soil. We wanted to compare studies using alternate lab methods, certified reference materials to validate the PXRF measurements and show correlations. We reviewed the brands used, testing containers, testing times, homogenation, testing modes, testing locations, um, and testing locations used among the research reviewed, and we tried to determine the best methodology, limitations of PXRF, and gaps in research. So the way that we selected literature, we used Google Scholar and Web of Science to search for content related to PXRF, and urban soil research to search for peer-reviewed studies that used alternate lab methods or certified reference materials for validating the PXRF measurements. We reviewed literature spanning from 1990 to March 2024, filtering out non-relevant or repetitive publications with the ending. Oh, the graph is a little outdated here, but we got 87 articles in the end. So we ended up discussing, of course, the accuracy and precision influenced by various testing methodologies, and we concluded some of the methodologies that seemed optimal based on results that different people got, as well as the strengths and limitations of PXRF. As far as the instrument type, the most popular brand of instrument was definitely the Olympus NFX systems, followed by the Thermo Scientific Niton, which is what we use in our lab. There wasn't a clear impact of the age or brand of PXRF on the accuracy and precision of the readings in the studies that we reviewed. As far as calibration goes, certified reference materials were really popular. Several studies used these to calibrate the PXRF instruments. Um, and alloy chip clip calibration was also very popular. It involved using small discs or chips made of the same alloy or metalloid as the sample being analyzed. And the discs and chips are measured by the PXRF to establish a calibration curve for the specific metalloid. Other studies use the NIST reference materials, and also some studies applied correction factors. Um, we did note we did notice from a lot of the articles that the use of correction factors did significantly improve the reliability of PXRF measurements, especially when compared to methods such as inductively coupled plasma. It's effective for adjusting for discrepancies in readings due to factors like soil composition and contamination levels. Uh, as far as the There weren't any significant improvements between specific calibration methods, though. But of course, careful calibration is necessary for accurate and precise results and recommended. Glass introduced several elemental interferences. One study found that low density polyethylene resulted in minimal interference, making that material suitable for accurate PXRF measurements. So we use these small low density polyethylene plastic bags for testing our samples in the lab. It was also revealed that the number of polyethylene layers, as they increased, it negatively affected the detection of elements. So as far as using things like this film in these little cups, it's definitely best to keep it as minimal as possible. Otherwise, you will get some interference. Ziploc bags with blank corrections and plastic cuvettes were used in another study. And uh, so another study, they used the plastic bags similar to what I mentioned, and a lot of people use blank samples, of course, and corrected for the measurements they obtained on those blank samples. And some people used, one study found that external films in windows, such as Captain and Mylar, actually um, affected the readings and negatively affected the readings and attenuated to scatter radiation affecting analysis, which that is something that's really popular. So I thought that was an interesting thing to note. So the PXRF, it comes with factory calibrations. You can use mining mode, soil mode. There's also something called geochemical mode. But mining mode, some studies did use mining mode, even though these were soil studies. So it is important to note. But mining mode is tailored for heavy elements, um, especially geological samples like rocks and ores. Features higher voltage and lower current to detect elements at higher concentrations, and it's ideal for detailed quantification of high concentration samples. Soil mode was specifically developed for analyzing soil, sediment, and dust. It employs a specialized calibration model to enhance the accuracy for light elements, and it provides broad, easy coverage for detecting low concentrations. As far as testing time goes, studies use 20 seconds to 5 minutes exposure time per sample. They did find that the longer exposure times weren't necessarily necessary after 90-second tests, especially with soil mode. Soil mode definitely cut down the um, time for time for analysis, especially. Well, yeah, basically after 90 seconds, there wasn't really any change for most of the studies, but one study found that 120 seconds exposure was most ideal, especially for elements at lower concentrations. As far as homogenization goes, grinding and sieving, of course, is highly recommended. It definitely improved accuracy for many of the studies. There was no noticeable difference in accuracy and precision between using different methods such as mortar and pestle versus mechanical grinding for soil homogenization. As far as sample preparation, oven drying definitely provided more accurate results than air drying, highlighting the importance of thorough sample drying. Recommendations limit sample layer thickness to 2 millimeter. So it's recommended to sieve to at least 2 millimeters with less than 20% water content. So some mixed results were observed in the accuracy and precision of in situ versus ex situ tests. Some studies showed poor correlations, while others showed high agreement. In situ measurements were more accurate and precise than the ex situ measurements, but still provided reliable results when benchmarked against traditional lab methods. This is likely due to the heterogeneity of soil during in situ measurements. And why does heterogeneity have this effect? Well, organic matter present, it typically leads to the overestimation of toxic metals, increased soil moisture, alters X-ray absorption and scattering, particularly affecting the detection of elements with lower atomic numbers. Analytical interference and depth limitations. Basically, the PXRF can only scan the top few millimeters of soil. So if you're in a place where there's just a hot spot, um, it can be hard to get a composite sample. Well, it's better to get a composite sample so you can have a better idea of what that area is like. So while PXRF is a great investigative tool that can help identify hotspots of contamination, oven-dried, well-mixed, and soft soil provides more accurate and representative results. Many studies did validate PXRF results using traditional methods. Correlation coefficients were often used between PXRF and lab results, and they varied by metal, with many studies reporting strong correlations. And here are some examples. In one study, there were correlations from 0.82 to 0.98 reported for a wide range of elements, strong positive correlations for lead in another study, 0.6 to 0.9. R values for PXRF in another study versus ICP methods range from 0.522 to 0.832, and R squared values for another study did range from 0.03 to 0.89 for urban soil contaminants. And some more examples. There was a noted underestimation in PXRF for lead and arsenic in one study, good agreement for certain elements, poor accuracy for others like cadmium, chromium, Hg, and arsenic for another study, demonstrated reliability of PXRF for major metallic elements in another study, highlighted the influence of moisture in organic matter. In another study, there was acceptable to high PXRF measurement quality for various elements, variability influenced by soil properties. In another study, integrated PXRF with visible near infrared technology and enhanced the lead prediction accuracy. Here is one study by Tian et al. In 2018. Here is a graph made from some of their results. They compared NC2 versus XC2, and these two were compared to samples that were sieved. And you can see that for for NC2 versus XC2, there is similarities between copper, specifically manganese, zinc, nickel's pretty close, and arsenic. Lead is a little less close, but for these, you can definitely see that overall the SEF samples consistently show higher concentrations of metals compared to the NC2 and XC2 samples, suggesting that the sieving process definitely does affect the measurement outcomes. So in our paper, we were really focused on heavy metals, but we thought it'd be interesting to look at studies that did talk about some additional elements. Here is this one study that we looked at, Caparel et al. 2018. This table was retrieved from their study, shows comparisons between PXRF and ICP analysis. And you can see that there are high correlations with R squareds greater than 0.90 observed for calcium, chromium, copper, nickel, lead. I forgot what the name of the element for SN is in zinc. I really apologize for that. And however, only the regression slopes and intercepts of copper, nickel, and zinc were very close to the ideal equation that they were going for. This was one of their sites. And they had another site where high correlations were observed for cadmium, copper, lead, and zinc. However, cadmium was very close. Ooh, I think there's a little typo there. I apologize. For another study, this was retrieved from Wu et al. 2012. The summary of the results from PXRF and ICP-AES for 60 samples from the Eriell River watershed. The XRF instrument effectively detected toxic metals like lead, nickel, arsenic, chromium, cadmium, copper, zinc, and Hg in soil, excelling at screening high concentrations of lead, zinc, nickel, and copper. However, less reliable for Hg, cadmium, chromium, and sorry, I can't see what that says. Annotate from presenter view. Oops. Proper calibration and verification are crucial for accurate measurements. So, just to review some limitations, while several studies have demonstrated the effectiveness of PXRF in measuring heavy metalloid contamination in urban soil, there are some limitations with the technology, some regulatory and safety concerns. Of course, the PXRF devices emit X-rays and they require specific safety measures to protect the operator as well as bystanders, and regulatory compliance regarding the use of radiation emitting devices is crucial. I had to go through training, which was very thorough. Um, it wasn't entirely difficult. So if this is something that you're interested in incorporating, definitely it's not very hard to get the training that you need, but I do feel like it was very thorough and helpful. So as far as like skill and experience, of course, well, I just said you need training. Interpretation of PXRF spectra can also be complex, especially when dealing with mixed materials or low concentrations of elements. And there are some detection limits. Um, it's detection limits for lighter elements like magnesium, aluminum, silicon. They're not as low as those achievable with laboratory methods like ICP or acid digestion. This limitation can affect the analysis of elements present in low concentrations. Of course, there's matrix interference. Organic materials typically cause overestimation of metal concentrations. Sand and mineral substrates provide more accurate results. In some of the studies, increased water content, of course, lowers the reported concentrations for all elements. Soil moisture causes errors due to absorption and scattering. So more than 15% moisture significantly affects the accuracy. And also there are instrumental and operational factors. So regular calibration and maintenance are crucial. Instrument drift over time can result in measurement errors, and there are some limitations in field applications, like I mentioned earlier. Analyzers measure only the top few millimeters of soil, so it limits the depth coverage that's there. So, in conclusion, PXRF, it offers real-time results, so very convenient in that way. Allows for immediate data acquisition, essential for timely decision making, especially for detecting hotspots. If you go to a site and you just want to see what's there, and even though it's less accurate to get the measurements in the field, you can definitely be able to detect the hotspots. Um, and I think that's pretty important if you want to do an investigative study of an area. Minimal sample preparation reduces the complexity and duration of analysis. Of course, the fact that it can simultaneously detect multiple elements is incredibly helpful. The accuracy and precision of PXRF are influenced by proper calibration. Studies have shown that using certified reference materials tend to yield the most accurate and precise results, and um, it's recommended to do uh, corrections. It does help. Um, Different calibration methods such as regression models, alloy calibration, statistical calibration, and the use of pure silica standards have been employed, with CRMs being the superior choice, and instrument choice varies based on availability and budget, and the age of the PXRF does not necessarily impact the performance. So that's good to know. But calibration, preparation such as drying, sieving, all those things definitely improve the accuracy and precision of PXRF. Um, Recommendations for future research: continue to explore calibration methods, optimize sample preparation techniques, and validate PXRF measurements against traditional laboratory techniques, and study the relationship between PXRF accuracy and specific elements. I also would like to see more studies on PXRF in urban soil studies used to measure things other than metals, because I didn't see a whole lot of that actually. And I feel like it would be really interesting considering I read a lot about there being less accuracy um, for elements that are lighter. So I think that would be a really great place to look. I want to extend my sincere gratitude to the United States Department of Agriculture, Natural Resources Conservation Service for funding this research. And I want to thank you very much. And please let me know if you have any questions.
Thank you very much, Eriell. I appreciate you sharing the slides. Uh, you can see maybe a Q&A if it lets you
Mhm.
open. Does it let
Okay,
you
it
open there a
might
couple of
close
questions?
my
No, it's fine. You can close it unless people will want
okay.
to go a specific slide. If you click Q&A, there are a couple of questions there.
Oh,
Cassia is asking about organic matter.
increases. Is it known why organic matter increases the detection of heavy metals? Are there ways to test for heavy metals in organic soils using PXRF, or is it recommended to use other methods? Hmm. Well, I actually, I'm actually not entirely sure why organic matter increases the detection of heavy metals, and I don't necessarily want to theorize, but this is definitely something that I know I need to look into, and that's a great question.
I read before, I don't know if you came across this in the articles that you've read, Eriell, that it dilutes typically the concentrations of
Mm,
metals. The organic matter, um, because it's presumably contains less concentrations of the trace elements, unless we need to think what type of organic matter it is. If it's contaminated compost, then it would increase the concentration of heavy metals because it's contaminated compost.
mm,
So, but typically organic matter is more of a dilution uh,
mhm,
in soil. And as there are ways to test heavy metals in organic soil using PXRF, the people I've seen articles not in urban soil, but there was some trials, experimental trials on people trying to use cellulose and like artificially they were spiking their samples, measuring in organic uh, really organic matter, and also in plant tissues. So it is possible. We need to have soil mode, plant tissue mode rather, and calibrate the instrument to detect lower concentrations. But the metal should be at much higher concentration in the matter itself to be picked up by an XRF.
mm. Thank you.
Uh,
This next question, uh, have there been studies measuring heavy metals on current industrial sites versus previous industrial sites that have been planted in trees, grasses, etc., assuming not much replacement of soil has been done? Yes, there actually have been, uh, there have been, I've seen a lot of studies on previous industrial sites, and sites that have been remediated. I haven't seen anything on current versus previous. So that would be really interesting to see. But that's definitely something that a lot of people use PXRF for, because a lot of people have been using it for remediation specifically. Would you
yeah,
like to?
No, it's interesting. It reminded me of my work in New York City. John's question. We analyzed a lot of samples in soil that used to be industrial sites in New York. There used to be like navy yards or like smelters. There wouldn't be a replacement of soil, but a lot of those areas were gentrified and they would add soil, or rather compost or mulch. So adding or grasses. So um, I think we could make a case, and if we were looking for specific studies, we would see that the concentration dropped because the addition of this organic matter, which is considered as one of the best remediation practices. Good question. The next one is
Do you see this tool being used to check backyard gardens or proposed school gardens, etc.? Absolutely. We actually, in our lab, Dr. Paltzova's lab that I had the pleasure of working in, um, we dealt with a lot of clients, and one of my colleagues, she was actually doing a study on doing a survey of our city, Lafayette, or my city, Lafayette, that I'm a resident of currently, and we got samples from people's backyards, front yards, and we definitely used it for testing their soil and giving them recommendations for remediation if necessary. And I definitely can see this being great for school gardens. We also my other research is based in Chicago, and we're doing something. We're looking at the suitability of parks for community gardening. So we've been using it for that type of thing too, just to see what's there. And the next question, could this also be used for evaluating heavy metals in biochar? I think so. I'm pretty sure. I didn't see any studies on it, so this would be a really great topic of research. What do you think, Dr.
yeah.
Love?
So it comes back to that heavy metal question and organic matter before from Kasia. It's probably would be related to how much if we think of heavy metals, like how much we have there, what concentrations, and the detection level of the instruments. Like for lead, our instrument that we had, which is since 2016, was detection limit is like 4 parts per million of lead. So maybe newer models can reduce it a little bit. So biochar um, would need to be packed a little bit. So whenever we work with organic matter, like moisture is important and porosity. So we need to make it more of a dense material to test it. And like one of the images Eriell showed, there was XRF cups, and if we would compact some biochar or a compost, anything inside, we can test and see what comes out. But the detection limit of the instrument and the concentration will determine how much we can actually detect. And for some elements that typically have high concentrations, like lead, maybe even arsenic, copper, zinc, we can for sure see it. It's problematic for mercury and cadmium because they have a low concentrations, and XRF does not pick up unless it's 10 parts per million. So each element also has a different concentration measure. So, yes, I think it could be done, and it would be really interesting research to analyze, because one of the, I think David Weindorf, Professor Dave Weindorf, did a research on using XRF and compost, and you can look up his name and see what he found. There was some interesting studies on that. And I also see a question in a webinar chat. Christopher is asking, can you see it, Eriell,
Mm,
in the other chat?
Sorry. Oh, there it is. In studies that showed differences in results between PXRF and lab tests, were differences mostly from amount of each metal or presence versus absence? Hmm. Well, I feel like from what I read specifically, it seems like it's more um it's more about the detection limits with PXRF versus those types of lab tests. For lighter elements, it can be harder for it to pick up on certain things. So, digested samples and well, other types of lab testing, I feel like just can be better for that sort of thing.
Yeah, so that's good. Really great question. We could see the different amount because some of the metals, um, well, depending on the method we use. If we use traditional ICP method, the ideal we're supposed to use hydrofluoric, hydro nitric acid, hydrochloric, and hydrofluoric acid, right? So there's three of them. But the HF acid is super dangerous to use, and a lot of times scientists use other extractions. And some researchers say we should call it not total concentrations, but pseudo total, because they do not totally digest the entire, maybe like silicate minerals that are present in the soil. So those extractants may not be strong enough. So there's the arguments that XRF shows better total concentrations. However, that comes to the detection limit, indeed, and in this case, we might, depending on the metals like mercury or cadmium, would not be picked up by XRF if the concentrations is 5. But for cadmium, 5 is high, because for like New York City, if New York State, I think 2.5 is the health guideline, but XRF will not pick up unless it's 10 parts per million. So this is where traditional methods would be more preferable to use. So we need to know what we potentially find in the samples, but XRF is definitely good for identifying hotspots, determining what samples we should collect on what areas, and if you really need to have detailed information and low concentrations for like, research purposes, it would be nice to pair it with the traditional methods and measure it on OAS or ICP-MS. If we want to understand it for gardening projects or like schoolyards, it's enough to know if the data that we get, even if it's a little bit imprecise, because we want to know if it's higher or lower the guideline. So if EPA guideline is 200 parts per million of lead for children playing in a bare soil in the playground, if we get 205, 200, or 210, or even 195, it's less precise, but it gives us very good understanding that the soil may not be suitable for children, or like barely meets this criterion. So I think it's also important to understand what is the purpose of the research, how precise we need to do, and if this is the goal, then it's good to pair at least to have subsamples tested on with traditional methods, and then calibrate the results with XRF if needed. Do we have any other questions?
Another
Okay.
a question from John. With this work in measuring PFAS or
Mm.
synthetic chemicals? That's a really great question. I didn't see any studies on PFAS specifically, but now I'm very interested in seeing because I like to know as well. What do
Yeah, I
you?
don't know. We would need to see what those like PFAS or synthetic chemicals, what are the elemental composition, and see if we
Mm-hmm.
can develop a proxy with XRF, because XRF is mostly measuring like inorganic, heavy, dense elements, and we need to see if any of those synthetic chemicals we want to test contain one of those elements, so we can at least have an idea what it could be in a sample. But yeah, this is a great question and really good. Maybe this is what I should propose for my next release.
Mm-hmm. Oh yeah, yeah. Mm-hmm. Because you have been talking about wanting to explore PFAS. I think that would be really great.
Interesting.
Uh, Another question. Thank you for the compliment on my review. Uh, the question is, are the considerations for measuring heavy metals in plant tissue similar? Are these
Mm.
instruments considered as accurate for plant tissues as they are for soils? I did see during my initial search for literature to use in this review that there were a good bit of studies on plant tissue. So as far as that goes, I know that there is research out there, but as far as the comparison between plant tissues and soils, I honestly do not know. But there's definitely some things that you can into, and I'd be happy to also look and see, because I did look at some of these things, and I'd be happy to look for those and send them to you if I do find them.
If you let us know, if you can send us
Oh yeah.
it
Yeah.
doesn't identify the name, but if you send us email, we can share some articles. I actually
Mhm.
know some colleagues in France who were testing herbarium. So they use the dry samples, plant tissue samples, and measure it with the XRF. It is possible but tricky, and there is no established protocol as far as I know. Some people work on it. It's really interesting. Some people analyzed like needles, some people test uh, tree cork. So there are some methods in development, but it's trickier because plants they have lots of moisture, and if sample is diluted, XRF will not pick it up. It's about detection limit. So ideally, we need to have a plant tissue that is dried. If you dry it, like crush it, and again compact it into like XRF cup, so increase density, so there's no porosity, no water, then we can measure it. And depending on the concentration of elements and the detection limit of particular instrument we use, and plant tissue mold, because the newer models do have some of them plant tissue. I think Bruker has a plant tissue. Then we can have a lower detection limit and actually test for it. So this is definitely another great research question, something I've been interested in learning. For heavy metals, mm, it's a little harder because of the concentration they need to measure in tissues. But if they were measuring like sulfur, it would be or calcium or iron, it would be easier to measure because those elements come out in higher concentrations. And yeah, so I think in even like Bruker website, not that I'm advertising for them, but there are some handouts that I saw previously explaining how to test plant tissues and some vegetables with them. So we could either do like rice powder, like rice and or cereal. We could crush it and make it a powder and
Mhm.
test it. So XRF does have implication for food quality, uh,
Mhm.
but it's not quantitative yet. Like to the extent, to some extent, but there might be in the last couple of years some new articles that popped up that I'm missing. But I think it's ongoing research with a lot of opportunities. But overall, we can use it to at least measure qualitatively. Okay, any other questions? Someone said great presentations. Thank you, John, and thanks for the answers to the questions too.
Thank you. Thank you so much. That means a lot to me. I really appreciate you guys showing up.
Yes. Okay, great job. Well, thank you everyone who came and participated and listened to us. If you have questions, feel free to email me with your feedback on
Mhm.
to the email that you received.
And I
Anyways,
can put my email in the chat
yeah,
as
Eriell, yeah, if you could type in, that's great. If you write it in chat, Eriell, feel free to ask us questions, give a feedback. We'll be happy to share more research and articles that we compiled. And if you have any ideas for research, I will be also happy to hear it. Now that I'm at Purdue and I'm looking for new projects, new students to hire, it's been a pleasure working with Eriell. She's very responsible. She's looking for a job. If anyone is needing great soul scientists in your office, feel free to
well.
um, inquire her CV. But yeah, it's been a
Thank you guys for all the great compliments. I'm reading the chat now. Thank you. It really means a lot to me. And I was really nervous because, the USDA funds my research, and I was really, I wanted to impress you guys. So that means a lot to me. Thank you.
thank you. I appreciate it. Yeah, it's always a pleasure. You guys are extremely supportive. Okay. And I will make sure to share a presentation, this recording, in a few days, and I will send it to my original email, and then your contact will share it again. Unless, oh, maybe a webinar will actually give me a list. If you registered, it probably has your email address, and I can directly email you the recording. Thank you, thank you, thank you. Well, thank you so much for coming. And again, feel free to stay in touch with us, contact us, and I'll see you around one of the USD conferences, meetings, or any other scientific endeavors. I appreciate your support and help with this project. Bye, everyone.
Bye.